You're smarter than that.
Alright, I'll start at the end.
Oh, I'm taking notes.
Energy. Okay. Beginning at the end.
Can you fix your board? Like, please.
Oh, that's gonna bother me.
I'm sorry.
What you have to never do, okay, so here's words by which to live. Never clean a whiteboard with water. Never clean a whiteboard with water. Always use solvent.
Salt.
Solvent. Solvent.
Solvent.
Alcohol is okay. It's not the optimal solvent. Okay.
Yes.
That's 1 minute exactly.
Okay. Here we go. Energy. I'm gonna assume lots of stuff. Like you kind of have the gist of it, right? Change in energy is generally 0. Okay.
Wait.
When do you use this? If all energy is mechanical. If all of your energy is mechanical, that means you've got this list. It's either it's GPE, it's kinetic, it's spring. Okay? If all of the energy in your problem, beginning and end, are these things, then you can do it this way. So, okay, our energy is not going to change. Energy at the beginning, energy at the end, it's fine. Okay? Otherwise, okay, so if there is friction, air resistance, non-mechanical energy. Okay? If you have a situation like this, right? So like there's a person who's pushing a box, well, we don't have a way to capture the energy of the person, right? There's not like an equation that says energy person equal to this. There's not a formula that says energy of friction, this. Energy of the air resistance. We don't have those formulas. So the way we have to conceive of the problem is to say, look, change in energy is work. We can capture these things through the use of work. And work is that. It's the force parallel to the direction of motion times the displacement, as long as the force is constant. Okay? So if F parallel is constant, so for like friction, this works great. Friction is a constant force, it's parallel to the direction of motion. You can just do the multiplication, you're good. Yes?
Can you also do like F times delta x times cosine of theta?
Yes, which is the same thing as this.
Oh.
That is literally equivalent to F delta x cosine of theta. To get the parallel component, you're going to multiply by the cosine of the angle. Okay, these two things are literally the same. Okay? As long as the force is constant, like friction, like air resistance, okay. If you have a problem with air resistance, it'll be constant. Okay? Or like in the mops, there were these problems where like a skier is being towed by a rope. That's a constant force. We don't have one of these equations to lean on, so we have to go to this idea of work to gather up the change in energy. Okay? If your force is non-constant, for whatever reason you have a force which isn't constant, for non-constant forces, we use this idea. You take your force parallel to the direction of motion, plot it against the displacement, whatever it is, you can deal with anything this way. The area underneath that thing is work. This works for either one, right? Because if you just did a constant force, it'd just be horizontal. So it works for either case, but if you have a constant force, you can just go here. Okay? If you're reading a problem and there's a graph with force and displacement on it, the area is going to give you work. Okay? about it. The rest of the game becomes just accounting for the energy. You read the problem and say, what kind of energy do I have? What kind of energy do I have now? Was there work done or was there not work done? Okay? And here's how you really know that. If all of it is inside what the, this thing about conservative forces in the mop is talking about those things, right? If all of your forces are conservative, that means you can go and do something and come back, and all of the energy is still the same. Those are conservative forces. So you're talking gravity, springs, they work that way. Okay? But if you're talking about friction, friction doesn't act that way. I can't take a ball, kick it up a hill, and expect it to come back with the same amount of energy. It doesn't. It loses the friction. They're non-conservative forces. Okay, so these are non-conservative forces. Again, if there's a person, I'm pushing a box, I'm doing work. We don't have a way to say how much energy I have in me that I'm doing the work here. And we can't get that energy back, right? I can't like get filled up with energy by letting a box push me, right? If I want to get energy into me, I gotta eat, okay? So once I do work, that energy is lost to me. It's not conserved in this way, it's in sort of staying useful, okay? Yeah, so that's it. The rest of it is an accounting problem. We use our LOL diagrams. Use these things, define your system. If you're in this case, okay, where there's like a rope doing some work or a person doing some work, they're gonna be standing on the outside here, right? So the non-conservative thing, you stick that outside, then you can have it either putting work in or taking work out, and that can work into your equation, okay? If it's going in, put it on the left. If it's coming out, put it on the right.
No. I've helped you guys enough. Now take it.
They're taking tests.
Then do it again.
It's the best time to teach is immediately before a test. Because people, they want to learn in that moment. 5 days before a test, they're like, whatever. The 5 minutes before a test, though, they're like, I will learn now. Have to take advantage of those things.
Which basically means all you have to do is teach them 5 days before a game.
Yes, I probably have as much luck with some people. Yeah, okay. That's energy.
Bye-bye.
Again, I'm assuming you've got the equations for these things. They're there. Great. Force of a spring, I'm assuming you've got that. Don't forget the negative. F spring minus K delta X. Leave it out.
It's gone bye-bye.
Why did it go bye-bye?
It's gone the wrong way.
Well, drink more coffee.
The problem, and you're just like,
When you drink coffee too slowly, your creamer goes bad. Okay, that's energy. That's it. There are a whole bunch of practice problems. Okay, here's the thing you should be ready to deal with. Just draw a picture. All right, so you got a box, and it slides down this slide and goes off the end. Once it gets right there, what is it?
it's free
It's free fall.
It's free fall. It's a projectile, right? Huh? Looks like a sweet FRQ, right? So back here we've got an energy problem, and then we've got a projectile motion problem, and these things flow together quite nicely. We couldn't do this before with projectile motion because we couldn't deal with this, right? We had no way of dealing with a slide that wasn't like just a ramp. But now we can actually deal with this. Because all you have to know is the height and stuff, and you can figure it out. You've got GPE here, and here you've got GPE and some kinetic energy. You can use that to figure out your velocity. And if you had, say, the angle up here, you could use that to then go answer a projectile motion problem. We'll talk about projectile motion, okay? But the concept is how might stuff show up in an FRQ? Well, something like this, right? Or a problem where you've got like, spring-loaded launcher of some kind.
Of course.
Right, so you got this spring right here, so you have elastic potential energy, and then it launches the thing that way, so that this becomes kinetic energy, and now it's a projectile. Right, so the problem starts energy, ends kinematics. Okay, so you should sort of have this concept in your head. This is a very likely thing. The end of your energy problem becomes the beginning of another problem. Okay. There's energy. Moving on. Kinematics. Let's go with this one first. This is an FRQ off the first test. So you got arrow 1, it's launched at a velocity. Straight up. Arrow 2 is launched with twice the velocity. Good. How much higher does the second arrow go? Four times. How did you answer that so quickly? Oh, you memorized the answer?
Wow.
Well, we'd be allowed to get one of those two, right?
Yeah.
Oh, okay, then I'm gonna do it. Well, why? Why would you do that?
Here's something to know. This is constant acceleration, right? I launch these things up in the air, that's constant acceleration. If you have constant acceleration, isn't velocity proportional to time?
Yeah.
Yep.
It's a straight line, right? So here's our VT. So look, something like that. There's V1. It's going to slow down at a constant rate. It's a straight line, so velocity is proportional to time. If I double the velocity, I should double the time. If I double the time, or how do I get this? Position time, okay? That's a parabola, isn't it?
Yes.
Parabolic. In this case, it's going to look like that. Well, if it's parabolic, then position is proportional to time squared.
Yeah.
Okay. So I double the velocity, that will double the time. I double the time, that will quadruple the distance.
Or you just draw the velocity time graph for both and just found stuff.
Or you just draw a velocity time graph. This is there. There's 2v1.
And you just
And you look at the areas and say, okay, well that's twice as high. This is directly proportional, so that's t, which means that's 2t. The slopes are the same for both of them, right? So if I start twice as high, it's going to take twice as long to get down to 0. The area of this thing is 1/2 v1t. The area of this is 1/2. The base is, well, that's 2 v1. The base is 2t. Well, there's your 4 right there. Okay? Either one of these works. Here's a third way.
draw the acceleration.
Oh, that's actually way better.
That's true, isn't it?
Yes.
At the top.
Here, they're moving, but they're not off the ground yet. They have kinetic energy. When they're all the way at the top, they're not moving anymore. All of the kinetic has become gravitational. Well, 1/2 mv squared is equal to mgh. So you're telling me that v squared proportional to h? So if I double v,
You put your
4 times h,
You're low.
there, we didn't have this when we did this the first time. Now we do. Okay, so which one do you have to do? If it doesn't say anything, if the question is literally just how much higher, nobody cares how you do it. Use energy, it's easy.
Yeah, energy.
make absolutely sure you read the questions. All the words, because the question might say, use a velocity time graph to show that. It might say, use kinematics to show that, right? It might specify which approach you have to take, and if you do the other approach, you're not going to get any credit. Okay? So make sure you actually read the whole thing. Which way do you have to know? Both of them. The AP might not specify, but it might actually insist that you do a problem in a certain way. Okay? I know that when I was in college, that was common on our exams. It was like, do this problem this way, now redo the problem this way. It was a common thing that we faced all the time. Okay? You have to know both, but there it is. And again, what we know from energy cannot contradict what we know from kinematics. We established all of this stuff experimentally. We didn't establish this experimentally. We used our experiment to prove it. Yes, sir. Now is not the best time. He probably has a minute. Yeah. Okay. Good. He'll be on video for perpetuity. Okay. So, we okay there? This sort of makes sense how you can approach this kind of problem? Don't you wish we knew all this stuff at the beginning of the year? Okay. Review stuff. Key points. Velocity time graphs are good. Yes, so there's a reason we do it in the order we do. Right? Okay. So velocity time graphs are good. The slope is the acceleration. The area is the displacement. That's a ton of information right there. If you can draw a velocity time graph, you're basically home free. Okay. Next situation. We shoot an arrow straight up in the air, VO. We shoot another arrow at 45 degrees at VO. Same velocity, same speed. This one shot at a 45-degree angle, this one shot straight up in the air. Okay, these are arrows. Okay. Which, we'll call this one A and this one B, so we have something to speak about. Which one gets to the top first? Making some space while you think. What approach would you like to use? You have an approach you would like to use?
It's the first, it's the same.
Are they at the
Not the same.
Not?
Here's why.
I'm
Velocity
saying
time
it's the
graph.
same initial.
Same initial speed. Same initial speed. We can't say velocity because their direction is different, right? Okay, so here's arrow A. Getting to the top, is that a vertical question or a horizontal question? That's a vertical question.
Oh, this is easy.
That's a vertical question.
Oh, wait.
Big take-home point. Why am I doing this problem? When you get to a problem with 2 dimensions, you have to do it in 2 dimensions. You must break everything into components and treat the directions completely separately. This introduces right here, by having that angle, now we're in a 2-dimensional problem, we've got to split this thing apart. Okay? We don't care about the speed, we care about the vertical velocity. So here's arrow 1, or A. We don't care about the initial speed, we care about the initial vertical speed, which is right there. And is that greater than, less than, or equal to that?
Less than
Oh, it's less than, so we're down here.
It's not more than.
So there's A, there's B. Which one gets to the top first?
Wait. B.
There's TB, there's TA, right there. When the velocity falls to 0, that's when it's at the top. When the vertical velocity falls to 0, that's when it gets to the top. By drawing this velocity time graph, we can see that. We know this vertical must be smaller than that one. Energy is not necessarily a good approach on this one, because time doesn't show up in energy.
What about power?
Power, not a good power question.
Is power gonna be on?
I did not write any multiple choice questions that have power in it. Will it show up on the FRQ? I don't know. Power is work over time. So that's all. It's the slope of the work
It'd be like
time.
force times distance over time.
Pretty much. That's pretty much it. Yeah. Let's just manipulate that formula. Because you have to have time, energy doesn't do well here. Okay. Time never appears in any of our work equations, so don't use it. Okay.
Well, what if you could check the initial energy? They would be the same.
Well, you could answer this question: which one goes higher? A goes higher. A goes higher. Why? Well, 100% of this kinetic energy is going to become gravitational. Not so here. This component is never going to change. You're going to have a chunk of this kinetic energy here that stays kinetic energy. It can't get as high for the gravitational, right? So your paths here, the one is going to go straight up, the other one is going to go out.
So,
It can't be as high.
So they have different tops.
They have different tops. The area here is smaller than the area there.
Yeah,
They got to have different tops.
I totally did. Different tops.
You there? Okay, makes sense? Okay, reasoning. Here we have 100% KE. Here we've got 100% GPE, but here there's a split. It's
50-50.
KE plus
64.
GPE. I don't know what it is. It's something about root 2 over 2
Oh, yeah. Just a little 30, 60.
squared. So it's
Why is it?
actually probably,
No, wait.
it's just,
It's
I don't know,
about
whatever.
45.
If you really want to do it, you can calculate that.
Why is
It's
it
only
split?
50-50 in it.
Why is it split?
Because it's still the horizontal velocity,
Oh.
VOX, does not fall to 0. Okay, so here's a question that almost everybody missed. At the top of the motion, which arrow is going faster?
Top.
B.
Yeah.
When you originally took this thing, almost everybody, to a person, everybody said they were the same.
Pretty sure I said
I didn't know there were
I'm
different
pretty sure I
tops.
said
Yeah, almost everybody said they were the same, and the reason is because you forgot about VOX. You were so focused on VOY, they forgot about VOX. Okay? So, for a projectile, big things, projectile stuff, split it up X and Y. You have to do it in each direction. Okay? Vertically, acceleration is 9.8. You can feel free to use 10. Just say you're doing it. Okay? In a multiple choice question, you're going to be close enough. Right? You might not get the exact answer, but you'll look and it'll be close enough. It'll be like, oh yeah, it's got to be that one. Okay? It's about 10. In this direction, no acceleration horizontally. Why not?
because there's no force acting.
No force in that direction. To get an acceleration, you have to have a force. There is no force horizontally.
Right into this.
There's only gravity. Gravity is vertical. It has the capacity to turn the thing. It has the capacity to slow it down vertically. It cannot touch the horizontal at all. Okay?
Considerably
See, why is
the Earth's mass.
Why is
is
the,
brighter, and then we
the
gravitate
bigger
to it.
velocity at the top?
Because the velocity here is 0.
I remember when I thought
It's the top for A.
Oh, because it has a
Unless
horizontal
the Lord's
up.
hammer was.
If you look at our Vx, there's Vxb, 0. Vxa, 0. So at the top, and big concept here, velocity is Vx plus Vy. At the top, both of these go to 0. At the top for A, that's 0 too, so the total velocity is 0. But for B, this hasn't gone anywhere. It's still whatever it was to start with. Okay?
Initial minus travel.
Kosher? Velocity time graphs, area, stuff like that. Good general stuff. General stuff about reading graphs that, you know, from the FRQs we have at the beginning of the year. Velocity velocity, time. You got one person doing this, another person doing that. Okay, so we got person A, we got person B. Are these two people ever going the same speed? When? When they intersect. This is a velocity time graph. The intersections, same speed. That's what the intersection means. Okay? You know what the intersection doesn't mean?
Same position.
Same position. You know, lots of you said on the first test. Same position. Make sure you look and say, what is this thing? What am I looking at? Okay? On a position time graph,
Then it'll be the same.
Now I see.
okay, so this is a position time graph. That means same position. Completely different thing, right? Here it's same speed, here, or same velocity even. Here it's same position. Different graph, same thing, different graph, different meaning. Okay? Okay, so how do we find same speed over here?
Oh, it's in the middle.
Somewhere in the middle?
Where the slopes are the same.
Where the slopes
So you just
are the same.
take the two positions and average them, and then that x values were the same as
Tangents?
Okay.
Sorry.
Okay, so there are two things here. How do we know when? So when, same velocity.
Oh yeah, we did.
Okay, when slopes are, that's what I'm telling you. Okay, so there are two definitions we need to talk about. We need to talk about average velocity. Average velocity is slope of secant line on position time graph. What's a secant line? Connect 2 points. Connect 2 points, right? So here and there. If I connect those, slope equals average velocity. That thing is a secant line. Okay? All of this like wrecked your guys' world when I taught you this the first time. Now you're like, oh, whatever, much fire.
What if you do two endpoints? Would that also be a secant line? Would it also be the same value?
We'll talk about that in a minute. Hold on, we're gonna get there. Okay.
No, tangent line is just one.
Instantaneous velocity, this is velocity at a point, is slope of a tangent line on position time. So you take these dotted lines at a place right there, slope equals velocity right there at that point. Okay? Tangent lines are hard to draw. They're hard to draw. Okay? So if you're actually asked to draw a tangent line on an exam, there's gonna be some like forgiveness. There'll be sort of a range of answers. Don't beat yourself up over it. But don't be terrible, right? Like if your tangent line is all like crossing the thing, that's not good. Okay? It should just touch.
You just draw a secant line and draw two arrows.
Yeah, okay, or you do this. Okay, so here's this rule. If
Geometry.
position time is a parabola, if you are dealing with a parabolic position time graph, then instantaneous velocity equals average velocity at the center of the interval.
Can you say what the pulses are? Average velocity and
Instantaneous average. The bar means average. Arrows instantaneous.
You can get that by taking two lines and then drawing an intersection and drawing a straight perpendicular line and then you know where the center is.
That's just drawing lines.
Geometry is fun.
Geometry is fun.
You're just drawing lines.
Okay, you ready?
There's like no math.
Rewrite all of this. Change V to A and X to V.
Change V to A.
V becomes A, X becomes V, and you've got another set of true statements, except they're about acceleration instead of about velocity. It's literally the same thing. How do you find average velocity? It's the slope of a secant line on the velocity time graph. Okay, so literally these same things, if you change V's to A's and X's to V's, you get another set of true statements that are about acceleration instead of about velocity. Savvy?
Yes.
Displacement equals area under the velocity time graph.
I remember that.
You get your equation sheet, there are some equations for those things. The proportionalities are really strong. The more I learn about proportionalities, the more I like them. Or like, how nice was that? We were able to just write down two proportionalities, right? Displacement proportional to t squared, velocity proportional to t, so we can then conclude displacement proportional to v squared. Like, that's really powerful. And then if I know what happened to one of them, I don't really care about anything else. I can figure out what happened at the other one. Okay? It's a very powerful thing. Okay? Proportionalities. If you don't like them, that's okay. Just draw graphs and figure it out. Don't memorize the wrong stuff. Okay? The area under the velocity time graph is not always a triangle. It's not always a triangle. Sometimes often it's a triangle, but it's not always a triangle. What shape is it? I don't know. You draw the thing and then you figure it out. Okay? Sometimes it's a trapezoid, but even if it's not, even if it's whatever, you can figure it out. Okay? It's always going to be some combination of rectangles and triangles, and you all know how to find the areas of those things. So you just do it. You figure it out, and you do it. There isn't like an algorithm. It isn't like completing the square. Right? They taught you how to complete the square. You just do the same thing every single time. Physics problems aren't like that. You sort of start the same way. There's a basic framework, but you just have to figure it out as you go. Okay? Kinematics. Oh yeah, I want to talk about this one so that we can get this idea. Like I said, I'm using the FRQs to A, B, velocity, time. Okay, student A says B is always going faster because the slope is steeper. That's the statement. B is always going faster because the slope is steeper. And what's wrong with that? It's accelerating
This
faster.
is the velocity time graph.
But if you're accelerating faster, you're going faster, aren't you? No.
Because A is higher.
I really wanted to answer yes.
Yes.
Just
The
because.
change, you are changing faster, but did that actually tell you where you are? No, it doesn't. Okay? If you want to know the velocity, you just read it off the y-axis. Okay, again, this is good news. We've learned a lot of things because I have your tests over there in a pile, and like that question wrecked us, right? 50% of the people got that question completely wrong.
Granted, a lot of people are gone now.
I can't let them go to you.
Wait, can't let us what?
I can't give you your tests and let you just like run around with them.
Why not?
Because someone gave
Because
it to
I'm
them.
using questions that in order to get permission to use the questions that are on the tests, I had to tell the people that gave me the questions that I would not release them to my students. And here's why. If our tests go up on the internet with answer keys, our tests are done. We have to get new tests. You know how long it takes to write an AP physics test?
9 days.
Yeah, days. It takes days of work. Okay?
Just said 9.
To redo that work every year, we can't do. And while I would love to be like, oh, my students wouldn't do that, it only takes one person to say, oh, you know what, I'm going to put this up on the internet, and now all of these questions are lost to us. Or we create a situation where it's like, oh, well, I know that all these questions are on the internet, but we're going to use them anyway.
Why don't we do like this study?
Sure, if you come after school while I put it in your hand, sure. Sure, if you come at lunch and you want to see it, absolutely. If you're here, yes, we can sit down and look at them, right? Do I want to take our time right now to pass out tests? No, right? But if you come in after school, sure, we can sit down and we can go over the exact questions. I'm going over the gist of all of them, right? Like we've covered now the entire first test and everything we did wrong, right? We haven't looked specifically at every single question, but all of the content you needed to get all of the questions right, we've covered. And we feel good about it, right?
Everything except for the algebra.
Who?
The algebra.
Well, that's the next test.
I feel like
That's the next test. So we're about to go into that. Okay, so slope. That's this stuff, right? Change the V's to A's, and you get the acceleration stuff.
Yeah.
So the slope here doesn't tell you the velocity; it tells you the acceleration. Okay. The area underneath here tells you the displacement. Okay. Those are the definitions. You use them. Draw a velocity time graph. You win. All right. Experimental design question. Oh yeah. Okay. Experimental design stuff. Important notes. Okay. If you are asked to draw a line or curve of best fit, extend it before your data and after your data. Don't stop when your data stops. Take it both ways all the way.
below the zero.
You just draw.
Go through it. Go through it, okay? Take it, literally, it's like I'm drawing a line of best fit. Put the ruler down all the way across the page. Through the axis, right, the whole way across. Extrapolate in both directions, okay? Well, one of them is called something else. No. Whatever, doesn't matter, okay? Don't stop with your data, that's the point, okay? It's literally a line item on the AP. Frequently, if there's a graph on the AP, there will absolutely be a line item that says, did they draw a line or curve of best fit? And very often it includes a statement that says they have to have extrapolated it both ways. You can't stop with the data, okay? That was a thing that happened on the first test. Telling you don't do it. Make sure you go both ways, okay? I'm working under the strong assumption that we can, at this point, graph. We can linearize, and we can find equations.
Make a square.
We've done that a lot. All right, if nothing else, we should have learned those skills. Okay. Very quickly, though, let's make sure we've got this. It's a parabola. How do you linearize it?
Where?
If you have a parabola, that's a parabola. If you plot, actually, it's got to go through, it's got to be that parabola. It's got to go through 0, 0, won't work, right? Linearize it, x squared. Okay, there's your parabola. Inverse, or a hyperbola. Hyperbolas look like that. 1 over x. Makes it a line.
One that's 1 over x and squared.
If you try this and it doesn't work, if it still looks like, so if you started here, you did this and it still looks that way, square it.
Just the bottom?
Just the bottom.
It doesn't matter.
You can actually do either one. Generally safer to do here. So if it failed, if you tried linearizing it this way and it fails and it still looks like a hyperbola, if it looks like something else, do something else. But if it still looks like a hyperbola, then square this. That'd be 1 over x squared. Okay? If you did that and then it came out looking like this,
Square root it.
then you would either square root this or
Square that.
square that. So if you were here, then you would square this.
Wait, it's probably better just to square root the bottom side. Be less.
Depends on the situation. Depends on what you're doing. Okay? But there's your third one. Okay? Generally, hyperbola, how do you linearize it? Take 1 over. Okay? If it's a square root, looks like that. You can square your y, and that should straighten it out. If you happen to be doing a plot of
Syllogism logic is the only logic.
Okay, so there's just a quick review. How do you linearize? That's how you linearize. Okay, great.
Birds can fly.
Other experimental design stuff. Okay, experimental design stuff that people have messed up. More trials is almost always better. So if the question is like, how do you improve this experiment? More trials is almost always better. More data is almost always better. More levels of the independent variable. So instead of measuring at 3 different places, measure at 10 different places. Instead of just doing it once, do the whole thing 3 times. The exception to that, well, the exception to more trials is if the thing you're measuring is going to get worn out. If you're measuring like the speed of a person, well, you can't do repeated trials of that thing because after the first time they're tired, and so you're not measuring the same thing the second time around. You have to be measuring the same thing. Okay? So if there's a situation where something is going to get worn out or busted or whatever, you can't do multiple trials. So don't say it. So then take more trials in between, right? If I want to know the acceleration of a person, instead of just measuring the time from here to here and there and whatever, only measuring it a couple times, we'll measure it a whole bunch of times in between, right? Measure their time and position like 30 times between here and there. That way you have more measurements in between. Yes, sir?
Calibration.
So we stayed within limits. If you had kept doing, like if we hung the spring off the edge of the table and you just kept piling on, yes, then you would eventually get to a point where you would break the spring, right? You stretched your slinky out so far that it just busted and it never went back. If you do that, well, you can't repeat the trials. You busted it, right? So you get the one go and that's it, okay? There's a really cool experiment that we're not going to do, but it's really cool where you stretch a wire and you stretch the wire, and then if you take the weights off, it goes back. But if you stretch it too far, it won't go back. And it goes so far before it actually snaps.
So
it's really cool.
It's like a piece of gum.
It's kind of like a piece of gum. Yeah, it turns out that a piece of copper wire actually behaves like a piece of gum. It's amazing.
Wait, you split copper wire?
You stretch it.
Wait, does its ability to be conductive
amazing.
decrease as you stretch it?
Probably. I haven't thought about that one, but absolutely, actually, because it would make it thinner.
Oh yeah.
It's thinner, so you get more resistance. But anyway, that's beyond the scope. That's AP2.
I'm excited to take it.
Make sure we got all that stuff. All that stuff. Great. Okay. Also, reading. The number of points you guys have missed because you don't read. It's not that you can't read. You don't read the whole question.
That's true.
You have to read every word of every question, and you have to read every answer choice.
I don't.
Okay? You must do it. People miss points because the question said you have to label something in a certain way, and you didn't. The question said you have to, like this, there's an experimental design question about a runner, and the question said all 20 of your classmates have to participate in the experiment. And then you wrote a procedure which only used 5 of them. Well, but the question said you had to use every single person, so you didn't meet the requirements of the problem. It's not that you were doing bad physics, you just didn't read the whole question, so you missed it. Okay? Make sure you read every single word. That's not a physics thing, that's a test taking thing. Okay? It's those little details. It happens on the mops too, right? You start reading that mop the 4th time through, and they change one word. Like, oh, I've done this problem 17 times, and they change that one word,
Or they say,
and you miss it again.
List all
or they say the
plus
wind is
fire.
due north, and I didn't know what that meant
Yeah,
for like
okay.
5 times. It's
Okay,
stupid.
so
Or when you think
that's what I'm saying.
it said list all,
When you're
all
taking a
possibilities.
test, you have to hurry. Well, no, you have to go fast, but you don't want to rush. Okay?
That's so dumb.
Rushing means you're being reckless. You're not actually reading everything. Don't do that.
Like, what?
Okay? Don't diddle-daddle around, but you have to keep moving, but you have to make sure you've actually read the instructions. You have to make sure you've actually read the entire question. Okay? You guys miss a ton of points because you don't read the whole question.
Is that
Okay?
convention to say due north?
Done. Yes.
Why?
Didn't
Just
make up
say
the
it's
convention?
going south. That doesn't make any sense at all.
Well, from the north.
Yeah, it's coming from the north. Obviously, that means it's going south.
Yeah.
But why
Okay.
would you say due north? That just makes it more complicated.
2D motion, 2D.
God.
Alright, we've already talked about projectiles a little bit. If there is a two-dimensional problem, you must split it into 2 dimensions. X over there, Y over there. In almost every question involving a two-dimensional motion, there will be some kind of a point given just for tipping your hat to the fact that you've got to split it up into X and Y. Okay? For treating the motion directionally, there are points to be had for that. It's also almost impossible to do the problem if you don't. Okay? You have to split it up. If there's a vector at an angle, break it into components. Just do it. Okay? Break into components. As far as stuff goes, so you have in here, you've got projectiles, you've got riverbed. We already spoke some stuff about projectiles. We okay with projectiles?
Yes.
Sort of? Okay. Important stuff about projectiles.
Ground.
Hitting the ground is Y direction, not X direction. Okay. There's this word range. It's the horizontal displacement. That's what range means. Here are a list of things that affect the range.
Initial speed.
The angle matters. Closer to 45 equals farther. The farther away you get from 45 degrees, the shorter your range gets. The nearer to 45 you are, the biggest the range is. You optimize at 45. Okay, and we extensively spoke about that. There's this interplay between the two things. Okay, range depends on that. Range depends on time. If you give it more time, it can go farther. Okay, the exception is if you shoot it so straight up in the air that you're not going forward at all. Right. So the limitation on this is shooting it higher, right? So increasing Vy. If you increase Vy, you will give it more time and it should go farther. But if you increase Vy at the expense of Vx, that's not any good either. So we can increase Vx, that'll work, okay? But these things, they're hooked together through the angle, right? That's this 45 thing. When you get past 45, you increase this, but you decrease that too much. Okay? Ways to increase your range. Yeah, that's about it. Other things you can do: increase starting height. If you start out higher up there, it can fall farther. If it can fall farther, it's got more time. If it's got more time, it can go farther. We already drew the velocity time graphs, right?
Yeah.
Basic formulas to know.
There's a formula sheet.
I know, but I don't like them. It's been a while since we have.
Velocity is AT plus VO. Displacement is 1/2 AT squared plus V naught T. Yeah, those are your basic ones. Displacement is also this one. You know what that is?
Average velocity times time.
The average velocity. It's also this.
It's this.
That's a trapezoid, right?
Yeah.
You'll find that that is the area of a trapezoid.
Yep.
That's the area of a trapezoid right there. That's a trapezoid. So of course the displacement is that. Okay? Here's a fun one when you haven't done.
No, the area.
There's a good one.
Make it easy on yourself and just split it up and see which triangle.
Well, but if you know the area of a trapezoid,
Yeah, but just sometimes you just
turns out, general rule, the more stuff you know, the easier everything is. Just general truth, right? So the more geometry I know, the easier it is to do math because I can just lean on the geometry I know. If I don't know geometry, I've got to do everything through algebra or everything through whatever. If I only know one thing, I have to take that path every time. If I know lots of stuff, I can use that stuff.
If you only know that,
So here are the equations. Where do we get this one? Well, if you take these two and eliminate time, you get that one. You know what else this tells us? It tells us that displacement is proportional to v squared. Did we already know that? And this is yet another showing of that concept. Okay? You can plot, there's another graph that we never did. If you do velocity against displacement, it comes out as a square root. That's all. We didn't do this. It works. We've seen this several different times. Okay? You don't actually need this ever because it's just those. Right? That's it. Okay? And plus, how often do we actually do numeric calculations? Not very often. Okay. Great. There's projectiles, riverboats. I don't want to spend a lot of time on riverboats. Here's how you do riverboats. It's a two-dimensional motion. You split it into x and y. It's constant velocity in both directions. The end. You draw a velocity time graph in the x direction, a velocity time graph in the y direction. The distance across the river is one of the areas. The other area is how far it drifted downstream. Okay? If you need to brush up on that, there's a simulation. Just type it into Google, it'll come up. You can play with it all you want. There are mops on the topic, right? So if you're like, boy, riverboats, this really ripped me up, go do the mops, go read about them. It's constant velocity in two directions. Okay? It's got a little bit of relative velocity. The river's moving. The total velocity is the velocity of both things added together. Okay? Great. Done there. Newton's laws. I think we've spoken of this before. There's a lot of stuff we know, we just need to practice. Okay? There were a lot of people that did not get through the practice problems that I gave for Newton's laws, and then it showed.
the Avery.
The Avery, yeah, the physics Avery.
I did that myself.
They're hard. Okay, so here's, how do you know you're done? How do you know you're done with mops? How do you know you're done with the
When
Avery?
you get it,
You can do them all, and you can pretty much do them without thought or pause or mistake.
Unless it's like really stupid, you think, oh no, I put a slash down.
Yeah, so careful with that sort of thing, right? But if you did it and you're like, oh, I finally got that one right, I'm gonna move on to the next one. No, go back and do it 3 more times. So not to where it's like, oh, I finally got the right answer, but like, okay, I understand how to do this problem and I can just do it. Yes, ma'am. Work, yeah, work. Oh yeah, work, yeah. We did already today. We talked about that already. We can talk about it more. Can we talk about work a little more? Okay. I'm going to. Okay. So I'm saying, how do we're doing Newton's laws, and I'm saying the best practice you're going to get for that, go back to those aviaries and do them until you can do them. Like really grind through them. I believe that the sort of understanding is there, your conception is there. What isn't there yet is the speed and the confidence. That only comes with practice. Okay? So go and do those things until you're confident with it. Okay? So here we go. Newton's laws. First law. An outside, unbalanced force is required to accelerate a system. That isn't the statement we're used to, but that's a better statement. Yes. An outside unbalanced force is required to accelerate, comma, right there. Okay, There's first law. Here's what we know. That coffee cup isn't going to speed up all by itself. Okay? And if that's true, what we're saying is that in order to accelerate, speeding up means accelerate. In order to accelerate, we need something to come along and cause it to accelerate. Okay? So we're making the statement. In order to accelerate, you have to have an outside unbalanced force. Well, is stopping accelerating?
Yes.
Yes.
It's accelerating negatively.
Is it acceleration?
Negatively.
Yes. Whether it's positive or negative, who cares? Is it acceleration?
Yes.
Yes.
But it's not deceleration.
It is not deceleration. If you read the word decelerate in a test, I apologize for the person who wrote the test. The word decelerate means slow down. Okay? Is that positive acceleration? Maybe. Is it negative acceleration? Maybe. It depends on how you define your system. Okay? Negative acceleration doesn't mean slowing down.
Deceleration.
It means your acceleration is in the negative direction. It could be speeding up, it could be slowing down. Okay? And we can see that. Here's our velocity time graph. There's positive acceleration, we're speeding up. There's positive acceleration, it's slowing down. This is why I hate deceleration. This is decelerating, that isn't. The same for everything is the same. Why is this one different than that one?
Well, because you have to inverse it because it's at the bottom.
Yeah, it's crazy talk.
It's unnecessary extra stuff.
Positive acceleration. The end. Okay? In order to accelerate, we have to have an unbalanced outside force. I didn't take dependence, and who are we missing? We're missing Mr. Glass. We're missing.
Attendance in the middle of.
That's it. Okay.
So you just do a column of
Yeah, you know. Okay. Okay. First law. There's all this stuff. If there's no force, there's no acceleration. If there's no net force, there's no acceleration. The end. If there's no acceleration, there cannot be a net force. Okay? Second law. F net equals ma.
Dude, it's mind blown. Friction. Net friction equals meters times area resistance.
That's got to be it. Okay.
We should test it. Maybe he found something new.
There it is. Okay. There's second law. This tells us all kinds of stuff.
F net equals ma.
This tells us the direction of the acceleration. This is a vector, right? That's a vector. The direction of the acceleration and the direction of the net force have to be the same. The end every time. Okay? That includes turning. So let's talk about turning. Is turning accelerating?
Yes.
Yes.
Yes, because it's changing direction.
And direction is part of velocity?
Yeah.
Yes. If your velocity changes, you are accelerating. Turning means your direction changed. If your direction changed, your velocity changed. You are accelerating. We did circular motion. That's acceleration. Is there a non-zero net force? Yes. There was a central, right? There has to be a radial net force. Okay? That's captured right here. Okay? It's captured in Newton's second law. Other stuff you need to know to deal with Newton's second law. Fg is equal to 9.8 times the mass. That's weight. Weight, force of gravity, same thing. It's 9.8 times the mass. You can approximate that to 10 times the mass. Other things you should probably remember, G is also big G, big M over R squared. Well, this is Newton's law of gravitation, right? So that's the thing, you should probably have that laying around. Fg is also big G, big M, little m, R squared. This is not the radius of the planet. This is the distance from the center of one to the center of the other. R equals distance
It says R squared.
From-
What's the difference from the center?
center to center.
Wait, does that mean that there's a single point in the center of the Earth that is everything's
Yes.
It's the most popular part?
Most popular place.
No,
Yep.
never.
Mass of one object, mass of the other object. Generally, we're talking about like a planet and the sun. So the sun is much bigger.
Wait, that's
Okay?
so confusing. There's one point why doesn't it? Sometimes
You're so
it,
confused.
What's the?
Friction.
I just realized it doesn't make any sense at all.
Kinetic friction. Newton's law stuff. Kinetic friction equal mu k
It doesn't make sense.
Fn.
Yeah, no, that's all you can say.
This is just a number, right? You have to measure it or it has to be given. It's fine. Equal, equal, equal. If it is in motion, this is the equation you can use. How do you figure out F net? You figure it out.
Is
Okay.
that never?
F normal, 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 normal.
Ha!
normal.
Just correct about
It's good.
Okay.
It's like that there's a
You gotta figure this out. This is not by default. A lot of people carry around this idea that Fn equals Fg. Sometimes
The surface.
it's
Not FG.
something,
wait, the
Is he
surface.
across from the surface?
something about, yeah, something about the surface, okay? You can't just program this in your head. I grade your test, right? I see lots of people write down, it's like, oh, Fn, they just put Mg in there. Well, sometimes,
Unless it's a box.
if it's on a ramp, absolutely not.
Just the one.
Yeah, you have to do
If there's like two boxes, you gotta figure it out. Yeah.
you do like the sine and tangent of
How big is the normal force? It's as big as it needs to be. You gotta figure it out every time. Okay? That's it. That's the end. Okay? Great. Okay, so there's kinetic friction. When do we use this? Well, if there's friction and if the thing is moving.
maybe it is.
Other kind of friction. Actually, yeah, hey, let's do the other kind of friction and we'll talk about that. Static friction. So there's friction and it's not moving. Less than or equal to. Static friction. Static friction is not a constant force. Kinetic friction is. We did this experiment, okay? The static friction gets bigger, 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 bigger. You break it, then you go to kinetic friction, it's constant. This is as big as it needs to be up to a point, up to that point right there. Once it hits that point, you break the static friction, it goes into motion, now we're down to kinetic. Mu s always greater than mu k.
I'm still confused on why it's center.
If we graph friction
I just been destroyed.
against time, we're pulling something from rest, okay? Pull an object from rest. Okay? And you measure this friction, what you find is that it'll get bigger and bigger and bigger, and then peak down. We did this in class. We made these graphs, we looked at them, we saw this peak, we did this. Okay? The static friction gets bigger. At this point, the object moves. Once it starts moving, the friction drops off to a lower value and levels out. Okay? Air resistance. Let's talk about air resistance quickly. Things you might need to know about air resistance.
Everything that about air resistance.
F air, also called drag or air resistance, okay? So, there it is, things you need to know. Proportional to air density. You go out to Colorado, they've got a fine baseball stadium in Colorado, and you'll find that the home run fence is way out there.
There's air isn't dense.
Yeah, because Denver, the mile-high city, is way up there. The air is not very dense. So there's not very much air resistance. What is a fly ball at Wrigley Field is a home run in Denver. Okay? Because the air is so thin that there's no resistance as it flies through the air. So they built the fence way out there to compensate.
That's cool.
Okay? You go to Wrigley Field and the fence is like right there. Okay? Well, because they're at sea level, the air is pretty thick. Right? So the fence is closer. You go to Denver, or Wrigley Field's actually in Chicago. Still at sea level. Okay, but anyway, that's not the point. You go way up in the air, there's not very much air, it's thinner. Thinner air, less air resistance. Air resistance is about crashing into the air. Less air, less resistance. It's proportional to cross-sectional area. If I'm trying to go through the air like this, well, there's all this air in the way. It's got to push all that out of the way, right? Well, if I try to go through the air like this, there's no air to push out of the way, right? How much air do you hit this way compared to that way? Well, tons compared to that. Cross-sectional area matters, okay? This is why we make arrows little skinny things, so that they don't crash into stuff, okay? Try to throw an arrow sideways, it doesn't work, okay? Football. Football spirals and it's pointy on the end, so it cuts through the air, right? You try to throw a football sideways, and it just crashes in the air, it doesn't work, okay? It's also proportional to velocity squared. Velocity matters a lot, okay? If you start going fast, the air resistance gets big really, really fast. There's this word, we gotta make sure we talk about it, terminal velocity equals max speed of falling object. Okay? This happens when Fg equals F drag. Once you're falling so fast that the drag is literally the same size as your weight, you stop accelerating. Your velocity becomes constant, okay? So this is, I mean, you gotta get going fast. Most of the time we're not dealing with this, right? But when does this kind of thing matter? Okay, if you're like jumping out of an airplane, right? You're jumping out of an airplane, your velocity time graph is not actually linear. When you jump out of an airplane, your velocity time graph actually looks more like this. And it's not a parabola. It's not any shape. It's a mess. This is what it is. Okay? It levels off. We call this point right here terminal velocity.
Is terminal the nine?
Nope. What you'll find is right here, the slope right at the beginning,
Is 9.8.
that's 9.8 meters per second squared. But as you go faster and faster, this drag gets bigger and bigger. So the net force gets smaller, your acceleration gets smaller and smaller and smaller.
Wait, would it actually be 9.8 or would it be more like 7.5?
Well, here it would be
These are like
9.8.
super high.
Well, you have to be really high for that because. Question?
I just want
Yeah, this don't memorize this. This is just putting out there so you know. Will air resistance show up? I don't know, but there are the relationships that happen. Hopefully they make sense. Okay, so there's pretty much everything you need for second law. Yes, ma'am.
Oh, okay. Oh, never mind. Never mind. Continue.
Third law.
what is what's the equal? What's the equal? 50 times 10.
Third law. F
50 times 10.
of A on B equals minus F of B on A.
You can also just do 50 times 10.
There's third law.
Yeah.
And I still get 100. So just take
If object 1 pushes on object 2 pushes back on object 1 exactly as hard in exactly the opposite direction.
What's the J?
Chains. Yeah. Every action has an equal and opposite reaction. That's great if you know what action and reaction mean. I don't.
Yeah, I don't either.
Yeah, they're these words and they have great meaning if you have like great physical understanding of a situation. But if you're like just learning physics for the first time, those words don't mean anything, right? And then you write like a nice internet meme about world peace or something and apply Newton's third law to world peace, and you're like, no. Newton's third law is about forces. Two things interact. There are two forces, one on each item, equal and opposite. You cannot hit without being hit. Every interaction is both ways, okay? Why don't these two things just cancel out? There's a little girl and she's like, oh, I have a wagon, but I'll never be able to move it because the harder I pull on it, the harder it pulls on me.
I have an example. When you see people on Walking Dead and knuckles are all bloody after.
I know.
They got punched in the knuckles.
Yeah, anybody that's ever punched anybody knows that there's a penalty to be paid for punching somebody.
Is it, do you have, is it because the girl has no strength and doesn't? So, I don't know. I got that question wrong.
No. Okay, so here's the girl in the wagon. Girl in the
I
wagon,
have no
ready?
idea how to answer this question.
Girl, wagon. Okay, so the wagon's got some weight. There's FN, right? That's fine. The little girl pulls this way, friction that way. Here's F girl on wagon. Okay? The net force on the wagon is F girl minus the friction. There's no third law pair here. To be a third law pair, it's got to be A on B, B on A. All of these are on wagon. They're all on A. No third law pair. If I want the third law pair, I've got to come over here. So we have the weight of the girl, the normal force of the girl, F wagon on girl. There's your third law pair. F girl on wagon, A on B, F wagon on girl, B on A. Opposite directions, equal size. This way, you've got friction. Okay, F net girl is friction minus F wagon. Why don't they cancel out? They're not on the same thing. That's why. To cancel out, you would have, this cancels that. Why do they cancel out? They're both acting on the wagon. This cancels that. Why? They're both acting on the girl. This does not cancel that. They're not acting on the same thing. That's why.
Yeah, I definitely got that wrong.
How are we able to actually pull the wagon? As long as the force of the girl is bigger than the force of friction, the wagon will accelerate. As long as the force of friction that the girl is getting from the ground is bigger than the force the wagon is putting on her, she will accelerate. That's the net force. You only add up forces which act on a single object or system. Okay? The third law pair, again, here's the third law pair. This force, that force. There's the third law pair. A on B, B on A.
I don't understand.
Okay? That's third law. Why is it useful? Well, it lets us bridge from one thing to the next. Okay? That's what third law does for us. It allows us to figure this out somehow and then go over here and figure out something else. Because we know this one and that one have to be the same because of third law. Okay? That's all. What do you need to know third law? Anytime you have two things interacting, the forces they put on each other are exactly the same. Okay? Opposite in direction, exactly the same size. Okay? Even if it seems like one thing is just passively receiving the force, it's still putting a force on. Okay? And I said there's a price for punching somebody. And usually if you like punch somebody in the head, odds are you're gonna break your hand. Like the end, especially if you've never done it before and you make your fist run. Okay? And it'll bust your hand up. Okay, you gotta wrap tight. You gotta put this on my leg. Okay?
Wait, okay, so how we dealt with this?
Okay, so
I'm having like a breakdown because I don't understand why everything goes to the center of everything. It's really confusing.
okay, so energy, so I think circles. Circles, circles, circles. You cannot have uniform circular motion in a vertical circle.
Because of gravity.
Only horizontal. You have to have net force radial. To get uniform circular motion, you must have a radial net force. In a vertical circle, gravity doesn't behave. It doesn't care about your circle. Gravity pulls down, not radially. Okay? So we can't have a vertical uniform circular motion. Horizontal, all day long. You have a string or something pulling it towards the center. An orbit, great. You have one force, gravity, it's radial. Done. It goes around the planet and it's always pulling towards the middle. Perfect. Okay? if you have something in uniform circular motion, or even close to it, the acceleration is v squared over r. There's a great video of some guy showing you that geometrically, right? We also measured it. We did the whole lab spinning things around. We got that same result, okay? It's true. You have uniform circular motion. AC is v squared over r. That's great. Force of gravity, we just wrote that down. There's a force. It's great, okay? Remember the r. Common error people make is they want to say the r is just the radius. Or they want to say the r, like with a planet, it's like, hey, the thing is 3 radiuses off the surface. Well, that means from center to center, it's 4 radiuses. You have to make sure you're actually measuring from center to center when you use gravity, okay? There's circles, Kepler's laws. Kepler's laws. Planets orbit in what shape? Ellipses, ovals.
Wait, Mr. Ross, I figured it out. It's Newton's third law. That's why it's in this.
Newton's third law. Good. Okay. So that's Kepler's first law. Second law. What? Equal area and equal time? Equal area and equal time. And reasoning, as it goes away from the sun, there's a component of the gravity which is pulling back against the direction of motion. Yes, ma'am.
Are you saying equal air?
Equal area. Equal area. Okay, there's the sun. As a planet moves from here to here, it slows down. As it goes from B to C, it speeds up. When it's way out there, it's going really slow, so it doesn't make it very far. So this area is kind of small. When it's back here, it's going really fast, so it covers a ton of distance around, but it's not very tall. So given the same amount of time, if delta t here is delta t there, the areas are the same. Same area. Equal areas and equal time. Okay? Called like the law of harmonies or something like this. Okay? And the other one, period squared proportional to radius cubed.
Yes.
And that's it.
I remember that.
Yeah.
We did a whole algebra thing. I don't remember it again. It's very proportional to R.
And I walked through this, I did this derivation, I don't know, 5 times?
You did it 3 times.
3 times? Okay, I did it a whole bunch of times, not gonna do it again. If you didn't write it down the first 3 times, you're not gonna write it down the 4th time either. Okay? You did a lab on this, right? We did the simulation, and you had to linearize the weird thing, and you had to keep changing stuff until it linearized. This is where it linearizes. You know what this isn't proportional to? Mass. Where's mass in this proportionality? Oh, it's not there.
Got canceled out.
Yeah, it got canceled out, doesn't matter. Okay? The time it takes a planet to go around the sun has how much to do with how massive the planet is?
Nothing.
Nothing to do with that. The only thing that matters is how fast it's going. The end. If you want to change the period of something, you change the radius. That's it. Okay? You want it to go faster? Well, its radius is gonna change, right? So there's that. The other thoughts. There's circles. I think that's it. That's all year, right? Skip anything? Yeah, did you do it?
Yeah.
Did you figure it out?
Yeah.
Make sense?
Yeah.
Okay.
And this energy is fine.
You're gonna find another sheet, yep. If you have some work, you gotta throw that in.
We submitted through the.
I won't even submit.
What?
Just hold on. Yeah, I got no time for more. It's okay. Good. You got anything? A lot of stuff. Yeah, let's turn this
No, I didn't get a chance to give it to you yesterday.